A circuit in which currents and voltage vary sinusoidally are called alternating current or AC current. All AC circuits are made up of combination of resistance, inductance and capacitance. The circuit elements RLC are called the circuit parameters. Now we will see the effect of all the circuits. First we will see the purely resistive circuit. Purely resistive circuit. This is a purely resistive circuit. There is only resistance. This is Vm, and this is the curve for Im, and this is the phasor diagram. As already said, when the current flowing through a pure resistive circuit changes, no back EMF is set up. Therefore, applied voltage has to overcome the ohmic drop IR. So, IR is equal to V. So, I is equal to V upon R, which is equal to Vm upon R sine omega t. The current will be maximum when omega t is pi by 2. It will be Im is equal to Vm upon R, and the instantaneous current value will be I is equal to Im sine omega t. Now we will find out the power in purely resistive circuit. Power is given by voltage into current, and here this is instantaneous voltage multiplied with the instantaneous current. The value is Vm sin omega t and Im sin omega t. After solving this, we get the value is coming out to be this. The average of this term is for positive as well as negative cycle will be 0. Therefore, power will be Vm Im upon 2, and this is the result. Power is V into I. We will see the effect of purely inductive circuit. The voltage applied here is Vm sin omega t, and the coil is of L Henry. Then the self-induced EMF in the coil is minus L di by dt. Since the applied voltage at every instant is equal and opposite to the self-induced EMF, V is equal to minus EL, where this is EL. So Vm sin omega t is minus of minus L di by dt. So di will be Vm upon L sin omega t dt. Integrating both the sides, we get I is equal to Vm upon L sin omega t dt, which is equal to Vm omega L minus cos omega t plus a constant, where A is a constant of integration, which is found to be 0 from initial conditions. A is found to be 0 for initial conditions, and I is equal to minus Vm omega L cos omega t, which is equal to Vm omega L sin omega t minus pi by 2. Current will be maximum when sin omega t minus pi by 2, when this term gets to be 1, ये वाला term जब 1 हो जाएगा तो current will be maximum, and that will be Vm by omega L. Im is omega Vm upon omega L, and XL is, which is equal to the reactance offered by the inductor. So XL is the reactance offered by the circuit. So from the expression which we have derived, it is clear that in a purely inductive circuit, it is observed that current lags behind the voltage by pi by 2. Okay, so power in a purely inductive circuit, power is V into I, and it is given by this. But power for the whole cycle is 0, but the instantaneous power, maximum instantaneous power, is Vm Im upon 2. I is given by dq by dt, rate of change of charges. Charge here is C Vm sin omega t. So the current is coming out to be Vm 1 upon omega c sin omega t plus pi by 2. There is a lead. Current is leading here. Im is Vm upon, this is the maximum current. Vm upon 1 upon omega c. 1 upon omega c is Xc, which is the reactance offered by the capacitance. Power of the circuit is V into I, and here voltage is Vm sin omega t, and I is Im sin omega t plus pi by 2. Solving this, we get this, and the average power of the whole cycle is 0. So maximum instantaneous power is Vm Im upon pi 2. This is the circuit of RL circuit, series circuit. This is the phasor diagram, and this is the waveform of voltage and current. In the circuit, the voltage across resistance is VR, and the voltage across the inductor is VL. V is the RMS value of the applied current, voltage, and I is the RMS value of the resultant current. Voltage, the applied voltage is equal to under root of VR square plus VL square. VR is a drop in resistance, it is IR drop, and VL is the drop in the inductor, so the drop here is I into XL. Now Z is given by R square plus XL square ka root. From the phasor diagram, it is observed that the current lags behind the applied voltage by angle phi. This is the angle phi. So to calculate phi, it is tan phi is equal to VL upon VR, and phi is given by tan inverse of XL upon R. So the value of L and R, it decides the phase lag. So power comes out to be this. So the average of for the complete cycle of this term comes out to be 0. So power is half Vm Im cos phi, which is equal to Vm root 2 into Im root 2 cos phi, which is equal to V into I cos phi. So this is the power of RL series circuit. RC series circuit, this is a circuit with R and C. This is the phasor diagram. Here we see that current leads behind the current by angle phi. This is the angle phi from here to here. This is the angle. This is the voltage. It is VR square plus VC square ka root. Solving this, it is IZ, where Z is root of R square plus XC square. To find out the difference, phase difference phi, we use tan phi is equal to VC upon VR, which is equal to XC upon R, which is equal to 1 upon omega CR. So phi is tan inverse 1 upon omega CR. So the phase difference between the voltage and current depends on the value of C and R. Power is given by V into I cos phi. This is the RLC circuit. R, L and C are connected in series. The drop in VR is I into R. The drop in VL is I into XL, and the drop in VC is I into XC. This is the phasor diagram of the circuit. This is the voltage and V of the circuit. VR square plus VL square plus VC VL minus VC whole square ka root. Simplifying it, we get IA into Z, where Z is R square plus XL minus XC whole square. So phi comes out to be tan inverse X upon R. If phi is positive, voltage leads the current. If XL is greater than XC and phi is negative, that is, when the phi is negative, it implies that the voltage will be behind current